Okay. Okay, welcome everyone. We are at day 8 and lecture number 16. So today I am going to discuss about the concept on designing bridge health monitoring. So far we have discussed about the methodology and a lot of things. In the first session also I discussed about the application of Bayesian probabilistic method for updating your prior information or your finite model, so that your updated model aligns exactly with your actual real life structure. So now the thing is that we need to put some sensor to obtain the response. Now, is it clear to you that a particular sensor can be used for solving all the objective or for monitoring all type of efficiency in the structure? Like as I said, due to earthquake or due to some other natural disaster, there is different type of damage, and there is also damage due to fatigue because of the live load. Also because of the environmental factor, there is a corrosion. So if I want to evaluate earthquake damage, so where to place the sensor, which type of sensor to be placed, so those things should be discussed. Then if suppose I want to detect the fatigue crack or fatigue damage, then what type of sensor should be used and where to place and what to measure. So those things should be discussed also. Otherwise you are putting some sensor and evaluating something else, then your objective will not be fulfilled. So it should be having clear understanding that what type of response that you want to evaluate and what type of sensor that you need to install in the target structure. So if you think about the bridge environmental condition or loading condition, then based on the loading condition, the bridge environmental or loading condition could be categorized into two categories. One is the extreme loading condition, another is the in-service condition. There are two possibilities. Okay, because of this two type of thing, damage are occurring mostly, except for corrosion, where because of the moisture or environmental factor it is occurring. Okay, so what is extreme loading condition? It is during the scenario of earthquake. Suppose there is a major earthquake happening. Okay, so it may occur at any point of time. Okay, you cannot predict the earthquake, right? So when there is an earthquake, then what is happening? There will be kind of natural disaster. Okay, it will shake the entire structure. Okay, in a if it is a very large earthquake, then the shaking or intensity of ground motion will be very large. So that will cause significant amount of damage in a particular structure. So in extreme loading condition, the main disturbance or factor is the earthquake, and to evaluate the damage due to earthquake, we may measure the response of displacement or inelastic strain. Why inelastic strain? Because during earthquake it will go to non-linear stage. We usually design any civilian structure as a earthquake resistant structure, not earthquake proof design, right? Why earthquake resistance? Because we allow the structure to go to a non-linear stage, so that our cost of construction could be minimized. Otherwise, if you only design for linear, then you need very bulky column or beam. Size of beam or column will be very large. Okay, as you can see, the old structure, we have designed the old structure, maybe 100-year-olds, all are bulky. You can see in BHU also, there are very bulky column or wall and other component of structure could be seen. Why? Because that time the uses of steel was limited and we wanted the structure to be in linear zone only. Okay, that means we did not allow the structure to go to non-linear stage. Okay, so now because of the reinforcement and other thing, we have that kind of trust or some kind of confidence on the structure that it can go to non-linear stage, because we are using steel, which is a ductile material. Okay, as you know, steel is a ductile material. So it can buckle before going into the fracture or complete collapse. Okay, so during earthquake we allow the structure to go to a nonlinear state, and by going to the nonlinear state it dissipates some amount of energy because it deforms extensively, and that way it releases the earthquake ground motion. Okay, otherwise if it is not permitted, then what will happen? Because of the earthquake there is a accumulation of stress, and then probably there will be some major damage, even if you design for larger bridge component or structural component. Okay, so the thing is that during earthquake we need to monitor the displacement and inelastic strain. And where do you evaluate the damage? Damage basically occurs in the form of buckling. Sometimes buckling occurs, okay, because of the compressive force, you know, the buckling occurs. Then because of the yielding, because we allow for inelastic deformation, it may happen that some of the structural, basically for moderate kind of earthquake we design in such a way that there is a damage in non-structural component. Non-structural component means those components which do not carry the vertical forces or self weight. Okay, so those buckling could be permitted, yielding could be permitted to those members. Then breakage of bearing. Okay, for severe earthquake probably there could be some other damage, okay, possible damage, but it should not collapse. Okay, so therefore we use some reduction factor. If you design the structure as per the IS code, okay, 1893, then you will see there is a response reduction factor R. Why it is there? Because we want the structure to be ductile. Okay, we reduce the amount of base here. Okay, so these are the evaluation criteria. On the other hand, for in-service condition, okay, what is the thing is happening? The main disturbances are the live load, means traffic load, vehicle load, or in structure it is the human load or some other load, okay, which are changing over time. And temperature. Temperature also causes lot of distress in the structure. Because of the high temperature it causes expansion. Because of the cold temperature in very cold region, there could be strain hardening and some other kind of thing, and possible damage could occur because of that also. So in that case we usually interested in monitoring the strain and displacement, and damage are evaluated in the form of fatigue, corrosion and loss of bearing function. Okay, these are our potential area or hotspot. Okay, so suppose I want to design monitoring system for extreme loading condition. I want to detect the extreme loading condition. Then what should I do? Where to place the sensor? That is the question. Should I place the sensor in a conventional way like nodal parameter identification, or we need to do something else? Okay, so that will be discussed. So for example, I will discuss this as an example of bridge. Bridge is kind of one of the critical structure. Okay, it requires lot of money, lot of funding and lot of time also to construct a bridge. So we should discuss this essential infrastructure for our GIAN course, which is sustainable structure. So while designing monitoring system, as we have already discussed, there are two loading condition. One is extreme loading condition and then in-service condition. For extreme loading condition, we are interested in knowing what will be the damage. Okay, because for major earthquake, definitely we are allowing some damage in the structure. Then the question is where the damage will be occurring. Then what is the sequence of damage? If there is a sequence of large earthquake, or earthquake is there for substantial amount of time, then not only one member but subsequent member will fall, or there will be damage in subsequent member. So which one will be damaged first, and then how the damage will be propagated? So that things we are interested in knowing. Then based on this failure mode and sequence of failure, we can have a monitoring system. Okay, unless we don't know where the failure will occur first or what will be the progress of the failure, we cannot implement a monitoring system. arbitrarily we can place a sensor, but that will not fulfill our purpose. Is not it? So from the common sense also we can say. So what we should do to arrange the sensor? So as you know, earthquake cannot be simulated for actual structure. Of course, for laboratory scale model you can have a small prototype and there is a sec table, okay, which is also very costly. You can simulate previous earthquake, okay, because earthquake are usually measured by some Richter scale and some other devices, and so you have a seismograph basically. So you have that record, so you can input that record in the complex actuator system that the sec table is having. Then you can simulate that ground motion in sec table, and then you can fix the prototype structure on the sec table and it will vibrate in a similar way. So that is only possible for model type or lab type prototype structure. But in actual real structure we cannot simulate earthquake. So what should I do for actual structure? So one thing that is possible is that you build the finite element model of that structure, okay, in the finite element software, of course, full scale model, okay, whatever it is there, full scale model, and then you run the earthquake analysis or seismic response analysis, we say, in using the actual ground motion, okay, some large ground motion, okay, high magnitude ground motion or high intensity ground motion. Then you can see how the response is coming. Then you can identify the hotspot, means where there will be possible damage, what will be the progress of failure, that we can identify. So that process is called fault tree analysis. Fault tree means how the parts of various structure or a particular structure is falling one by one, okay, one after another, okay. So that can be done. So simulation with FEM and fault tree analysis. Based on this result, then we can propose that these are the vulnerable points. We can place the sensor at here, at this location and that location, okay. So this will be applicable only for monitoring the earthquake related damage. So why we need this? Suppose there is a major disaster. Now during the major disaster, you see many structure will collapse, many casualty will be there. What we want to see that important structure, means hospital or colleges, school building, these are important structure, they should not collapse, because for example there is a class going on and probably there are 100 students in a single classroom. So if there is a disaster and the building getting collapsed, then there is a loss of human life, okay, large, okay, is expected, large amount of human life is, number of human life is expected. So we want our important structure like dam or some nuclear facility or fire fighting system building, okay, or all other police station, probably hospitals. So these are all important structures, or government official building, okay, those to be safe even during the course of major earthquake. So even if there is damage, or bridges, if bridge is getting collapsed during earthquake, then connectivity will be lost. Then how to send the ambulance or relief vehicle, okay, so that is a problem. So we want to know during or after the major earthquake whether there is a damage or not. Quickly we want to know, okay, real time, whether there is a damage in the important structure or not. Okay, so if there is a damage, then you send your maintenance team there, okay, to check whether what is the extent of damage and whether it could be maintained or repaired quickly, okay, within the limited time. So for that we need to place the sensor very judiciously, logically, okay, where the possible damage will occur. So I will give you a simple example in the form of bridge. Then I will go to in-service condition part. Oh, sorry, I forgot to discuss the in-service condition. To monitoring the in-service condition, what we need to monitor? We need to monitor the temperature, because in-service condition damage is caused by temperature, or the live load means vehicle. So if you monitor the number of vehicles traveling on a bridge or the variation of temperature, then you should be able to evaluate the fatigue damage. Okay, then based on that you can either redesign or retrofit to enhance the capacity of the deficient bridge component or structural component. Okay, So that is easier things. Okay, it's very clear. But in this case, it is not clear for particular structure. Suppose this is the sequence of damage. This is the particular location where the first damage will occur. But for another structure, probably scenario will change. So it depends on the type of structure as well. So I'll give you an example with the help of a girder bridge. Suppose this is a girder bridge, entirely steel girder bridge. Okay, this is the bridge which is in existing probably in Japan, which is 35.8 meter. Okay, real life structure. Okay, real life bridge. There is a pier. Okay, and there are three girders, G1, G2, G3, and all the components of this bridge has been modeled. Not only slab or girder or bracing, everything, including the bearing. There is a bearing now. Always we use elastomeric bearing at the bottom of the bridge, so that the substructure and superstructure is separated during the earthquake and to prevent the subsequent damage in the superstructure. Okay, so this then there is a question how to model the bearing, because the behavior of bearing is very complex. You cannot predict. Okay, so this behavior is non-linear kind of, because there is a rubber steel plate and combination of rubber and steel sheets, and it is behaving in non-linear fashion. So major dissipation of energy should be at the bearing. It should dissipate the energy as much as possible. Then rest of the thing will go to the superstructure. Okay. So therefore we say base isolation, kind of isolate the base. Okay. So not completely. So this type of bearing was modeled, and in finite software it was used MPC beam and some bushing connector, and this type of bilinear behavior is there. It is non-linear. Basically it is very non-linear complex, but to have a simplified model in Abacus, this type of bilinear model was considered. And this is the very high intensity ground motion that is used in designing important structure in Japan, level 2 ground earthquake. Okay, so which is having very high amplitude. You can see the acceleration goes to 800 centimeter per second square. Okay, very large earthquake, level 2. Okay, so if you test your structure against this earthquake, then probably if it is satisfying the criteria of their coral provision, then it is safe to use. Okay, if it is failing, then you have to re-design. Okay, so this is the fixed side of the bridge, and this is the free side of the bridge. So for what we did, we have inputted the ground motion at the base of the pier, right? Here, this is the pier, because pier is the fixed at the ground, right? Earthquake always comes through the ground, then it propagated through the pier to the bearing and then superstructure, right? So we inputted the earthquake ground motion, these two ground motion, northeast and east to west, means bi-directional ground motion at the level of pier. Okay, then we monitored the displacement in the transverse direction. Okay, suppose this is the bridge, we monitored the displacement in transverse direction, how it is behaving. Okay, so we can see after a certain point there is a relative deformation between the girder and the pier started to appear, probably after 3.1 seconds. Okay, when it crossed certain displacement value. So basically what is happening, suppose this is the kind of bearing, and near bearing there is a side block at the distance of 10 mm. The gap was 10 mm was kept. Okay, and then there is a side block was designed. Similarly over there, both way in the transverse direction. So the objective of the side block is to resist the transverse movement of the bearing during the earthquake. Okay, because of the ground motion, there will be vibration and it dissipates by deforming. So as much as possible, it resists the transverse direction ground deformation. So that is how much? The gap between these two is only 10 mm. So if it is beyond 10 mm, that means at that point the fracture of side block occurred. means it is no longer able to resist that movement, right? So why it is designed to fracture? Because we want to dissipate also some energy. We are allowing something to get damage. So when there is a damage, it dissipates also energy by getting into damage mode, right? Right? Otherwise, if you are allowing not to get fractured, then what will happen? It will try to resist, and whenever you are something trying to resist, then there is the accumulation of stress. Okay, so stress will be very large. Probably failure of bearing could also occur. Okay, to prevent that, we allow the side block to be broken. Okay, in excess ground motion. Okay, and that is happening over there. So you see the girder and pier. Girder is at the top, pier is at the bottom. So they started to now having some relative deformation. That means side block which was resisting is no longer is there. Okay, once it is broken, there is a relative deformation between the substructure and superstructure. Okay, so therefore it is happening. In the longitudinal direction, means if this is the bridge direction, this is the longitudinal direction, in this direction, there is no such relative movement because this is fixed side. Fixed side, it is fixed now in longitudinal direction. So no relative deformation is allowed. Okay, only transverse direction we have allowed some movement. Okay, and there is a side block. Okay, so what is happening there? First, there is a breakage of side block. Then what is happening? Again we inspected this. Okay, under the same ground motion. Once you got the result, you inspect one after another. Okay, so what is happening? We check what is the stresses accumulation. We see that the stress accumulation is highest at the lower end of the bearing. Okay, this is called bearing stiffener. Bearing stiffener. Okay, vertical stiffener on the girder. So you see, after a certain point now, 4.62 seconds, there is a buckling of that member. Not buckling, yielding actually. Yielding. Why yielding? Because you see the elastic strain crosses 0.2%. Okay. Okay, as you know, the yielding is defined as a stress corresponding to strain of 0.2%. So at that point, there is a crossing of that strain. Okay, so there is a buckling, yielding occurred of the bearing stiffener. So we noted down the time, 4.62. Then, of course, because of the fixed side, it is fixed, so stress accumulation is higher on the fixed side. Because it is free on the roller side, the stress accumulation is lesser. So you can see the elastic strain is higher for the case of fixed side and lower for the case of free side. Okay. Now, what else? We also inspected the bracing member. Okay, so after the yielding of the bearing stiffener, now bearing stiffener are connected by some bracing member, horizontal bracing, diagonal bracing, cross bracing. Okay, so those different type of bracing are there. So among all types of bracing, what we can see the strain in the longitudinal bracing member, horizontal bracing member, this bracing member, which is connected to the bearing stiffener directly. Okay, so that is crossing the yielding stress or inelastic 0.2% of elastic strain. So that is the moment it is getting yielded. Okay, so the sequence of failure is occurring like first side block, then the bearing stiffener, then it is the this horizontal bracing. So failure of stiffener lead to the buckling of the wave and subsequently the buckling of the horizontal bracing. Okay. Then, so if you summarize this type of analysis, okay, then you can have a fault tree of a particular structure. So this is for the bridge. Similarly, you can have different other type of bridges, different other type of structure. You can do similar type of study. For the case of building, you can have an input earthquake at the base, at the foundation. You run the seismic response analysis in the finite element software and then note it down where is the stress accumulation is higher or displacement is crossing the permissible limit. Then you have a sequence of failure. So here first ground movement is occurring, then shaking of pier is occurring, then shaking of substructure is occurring, followed by the breakage of the side block, and then buckling of bearing stiffener on fixed side of the bridge, then on the free side, okay, then buckling of horizontal bracing on the fixed side. These are called primary damage. Then if again there is a earthquake, or still you are having high magnitude earthquake beyond this, then what will happen? Then subsequent further damage will occur. So further exceeding damage, there will be pounding effect. Pounding effect means over there. So where there is a connection between, suppose one bridge is there and having multiple span, okay. So what will happen? Then this gap, there is a gap now between the two span. So there will be breakage of there, failure of that gap will be occurring because of the pounding effect, okay. There are two reasons. One is if earthquake comes, so probably first it will come at the, suppose it is coming through their side, so it will trigger the shaking of first span, then it will trigger the shaking of second span. So there is a timing gap, and because of that it is also happening. Sometimes it is also occurred because of the difference of natural frequency of this span and that span or something like that, okay. So because of these two things, pounding effect usually occurs. So further extended pounding will be occurring, and then expansion damage at sea, and then if there is further damage, then bridge will fall, okay, collapse, entire bridge will collapse. So we want, suppose there is a major earthquake happened, then immediately after the earthquake we want to know whether the bridge is safe to be used, because if the bridge is not safe to be used, we should immediately stop the vehicle, okay, movement of the vehicle, because I don't know whether we usually don't have the highway or expressway as a overhead bridges, okay. There are few just flyover kind of, but in Japan what we have seen, all the expressway now, all are majorly 80% are overhead, means those are all elevated, okay, bridges are there, not on the ground. So if there is a failure during major earthquake, some damage has occurred, they should stop the vehicle in real time by giving the warning message on the display board, okay, so that there is a damage and the inspection team is going there to inspect. So please don't travel. If you permit the travel, then further damage could occur due to the vehicle, movement of vehicle also, okay, in addition to earthquake. So these are the way you can design. So what we can design, what measurement system we can design for this. So in this study we have placed a sensor near to the side block, because side block is getting damaged first. So if you place the sensor at the side block, we will know that something has happened to the side block. That means integrity of the entire bridge has been compromised, okay. So that the time we should send our inspection team immediately, and we should stop the movement of vehicle on the bridge, okay. So to have this type of preventive measurement system or real-time monitoring system for monitoring the earthquake related damage or extreme loading event, then we should have the measurement system to be installed at the place where the location or damage will occur first, and then subsequent places also you should place the sensor, okay. For example, here we have placed the sensor at the side block. Then not only that, there is a cable running through the this bearing stiffener, as well as it is going to other side of the bridge. So it will cover the entire length of the bridge network system. So if there is any damage, okay, on any of the bridges, then that information should be sent to the bridge maintenance team immediately, okay. So that is all for monitoring the extreme loading event. Then I will move to in-service condition monitoring. So how to design monitoring system for in-service condition. So basically, as you know, fatigue damage is Yeah.
So placing the sensor, we will be able to place the sensor at the right position only if we have some certain knowledge about the how the structural forces are going on.
Structure.
How the transfer of forces is going in the structures. We have a prior knowledge of the structural elements where the elements where the which is the structural element or which is non-structural element. It is the only case we will be able to put sensor at the right place or
Yeah, that is what we discussed now. So you need to understand where the damage will occur first. So there you put the sensor. Then only you get to know after the major earthquake. See, during the minor earthquake or less significant earthquake, there should not be any damage. Okay. So if there is a major earthquake, then you should know where the damage will occur first. So we place the sensor there to just to know whether the damage has occurred or not. Okay. So that way you design the monitoring system. So you have to do this exercise for each type of structure. There is no general rule that for this type of structure you need to place sensor, or for every structure you need to place sensor at this place. Okay. So for each structure you do the fault tree analysis and then design your sensing system. Okay. Yeah, that is also possible. You have to do finite element analysis first. Then you locate where the stress accumulation is higher or possible damage is happening. Then you design your sensor system. Okay. Then coming to the fatigue damage or in-service condition monitoring. So as you know, fatigue damage is usually occur at the location where the multiple members are connected, right? Because that is the location where deformation of the member occurring from different direction because of the live load and accumulation of stress is happening. Okay, so those are the hotspot kind of connection. Always fatigue damage occur at the region where multiple members are connected. So for the case of this type of bridges, so what are the possible area? One is the cutout near the bearing, then sole plate. At the top of the bearing there is a sole plate. So this type of fatigue damage is occurring. Then also the vertical stiffener, upper end of the vertical stiffener. Then at the lower we are having gusset plate. Gusset plate we use to connect various type of bracing and member wave of the lower flange or the wave of the stiffener. Okay, right. So these are the connection are the hotspot for fatigue damage. So we need to also categorize which damage is caused by what type of stress. So this type of damage, like damage, fatigue damage at the cutout part or sole plate, is caused by primary stress. What do you mean by primary stress? It is by the cell point. Okay, it is there na cell point, and this type of damage is caused by primary damage as well as primary stress as well as the displacement induced stress or secondary stress. Now this type of stress, primary stress, could be overcome by designing the member in a proper way. Means you know the cell point of the entire bridge previously from the design. Then if you see the structural member is not performing well after 10 years, suppose you have designed the structure to be okay for 50 years, but after 10 or 20 or something, some period, you are realizing that there is a fatigue damage occurring at this spot. That means your member are not having adequate thickness or strength to resist the primary stress, means cell point. Okay, so you have not designed it well probably, that's why it is occurring. So you can redesign and you can use better member or better quality member, higher grade of steel or higher grade of concrete or higher thickness of steel, right? So that this type of fatigue damage could be prevented, because basically fatigue damage occurs because of the stress accumulation. So reversal of stress, where there is a reversal of stress and accumulation of stress, because it is designed for resisting certain number of load cycle. Okay, so basically primary stress means self weight. So you have not designed your member in a proper way, that's why it is occurring. So you should revisit your design and introduce some more efficient or proper design method, so that this type of damage could be prevented. Now the question is displacement induced stress. Can this be prevented? The answer is no, because there will be displacement always. Vehicle are moving always. Okay, because the main objective of the bridge is to allow the movement of vehicle. Now if you allow the movement of vehicle, so see, there will be deformation, and if there is a deformation, then there is a reversal of stress. Okay, vehicle is moving here and then another vehicle going there. Okay, so it is vibrating, it is like, so above the baseline some other load cycle, below the baseline some other load cycle. So reversal of stress is occurring. Okay, so that is the problem. So how fatigue damage is created? See, this is a simple animation, but it shows the movement of the joint due to traffic movement, okay, or bridge vibration. Now whenever there is this type of damage, see, there is a stress accumulation and it is also changing over time. Okay, the positive side or tensile side becoming compressive, compressed side becoming tensile. Okay, so changing over time, and because of this type of damage occurring. Okay, so yeah, so our study, our objective, before that, this is the real photo of a bridge and this is a real crack. Okay, you can see there is a crack. Okay, so same thing could be also understood through numerical analysis. So why it is happening? Okay, so there is a movement of vehicle, and because of this there is a stress accumulation occurring over a significant period of time, then it will lead to the fatigue damage. When the strength of the member is less than the number of fatigue cycle that is it is subject to, then what will happen? It will be subject to some kind of fatigue damage. Okay, so it cannot be prevented, but again you can enhance this. So suppose you know how many vehicles is running over a particular bridge. Of course, the vehicle information or vehicle data need to be collected. Okay, and also the demand on the bridge is also increasing year by year. Okay, because number of vehicle is also increasing. But if you install sensor and detect number of vehicle moving, also not only number but weight of the vehicle needs to be also identified, because then only you can identify how much deformation it is occurring. Okay, right, number of vehicle and weight of the vehicle. So based on this information you can evaluate how many stress cycle this member have gone through, or how many stress cycle this member is having or remaining before going into the fatigue crack. Okay, so if you have this information, then you can go to the site, retrofit those member, okay, right, and prevent the fatigue crack. Okay, or you can entirely replace that member. Okay, it is also possible in case of steel. Okay, you just loosen the bolt and remove some member and then replace with the new member. Okay, that is also possible. So objective is to know the deformation of the member under the live load. If you know the deformation of the member due to live load, then you know where the deformation is large. So there is the possibility that stress accumulation will be higher on those locations, is not it? So fatigue damage usually occur on those locations where the stress accumulation will be higher. Then you need to know, so that will help you to narrow down the checking part. So basically where the deformation is large, stress accumulation will be large, so we should always check those points. See, you should not check some other location where there is a lesser amount of deformation, right? So of course from common sense there will be less probability of getting fatigue damage. Okay, So this will not only help us to narrow down the checking part during the manual inspection, okay, but also help us to understand the structural performance in much better way, okay. And then it will also help us to implement a proper maintenance system or monitoring system, okay, so that this kind of fatigue damage would be prevented, because from the data we can know how many stress cycles that member has gone through and how many stress cycles it is still remaining before going into the fatigue damage. So what we need to monitor? We need to monitor the number of vehicle as well as the load of the vehicle, okay. So how to determine those things? Any idea? For real bridge, suppose there is a bridge, we want to determine how many vehicles is traveling and how many or what is the load of the vehicle. Is it possible to determine?
You can place some isolating material sensor below the luminous track. So when there will be pressure, there will be some electricity will be generated from there. We can get the vehicle.
Yeah, that is one way. Any other way? Yeah, correct, exactly correct. But any other way? Do you think? That is what he is suggested, weighing motion. Okay. Means one way is to transfer or divert the vehicle to your static weighing scale. Means dharam kata, you are saying na, roadside, dharam kata. So what is the purpose? To weigh the vehicle, okay. Okay. You can measure the vehicle weight. But that is not possible. For real scenario, you have lot of vehicle running in the normal service condition. So you cannot divert all the vehicle and have the measurement, okay. So what you can do, like he has suggested, you can place some sensor at the pavement, and from that sensor you can try to identify what is the speed of the vehicle, number of vehicle and weight of the vehicle. But there is a problem with that. One thing is that system, to install that system, you have to destroy the pavement and install the system. Then suppose you have done that exercise, you have completed installing the sensor. Now the sensor is also subject to higher volume of traffic load. Every now and then the vehicle is traveling. So vehicle movement is kind of creating some kind of abrasion, okay, the friction between the tire and the pavement. So that will cause damage of the sensor itself, okay. So you need to also protect your sensor. So after a certain point you will realize that sensor is gone. Also could be rainy weather, okay. So those should be waterproof. And again you have to have this wire and other thing also, wiring system, those things to be how to maintain those things. That is also a very difficult thing if it is on the top level, okay. Another is unbiasedness. So whenever driver sees something is installed on the road, then he will be alert. He will be reducing the speed or probably avoiding that portion of the road, okay. So that is also an issue. So that is not a unbiased estimation, okay, that becomes biased, okay. There are a lot of things. So to overcome that thing, there is another methodology which is known as bridge weighing motion. Just installing the sensor on the bridge, okay. So we convert the bridge to a weighing scale. You put the sensor at the middle of the bridge, underneath the bridge, okay, not the top, underneath. So no one can see it. And since it is underneath, it is protected from the wear and tear due to the vehicle movement. Also, it is protected from the water, rain, or other thing, right? So most of the limitation could be overcome, right? So what is the thing? This method is called bridge weighing motion. Okay. Before going to that, there is another slide. Now, why fatigue crack is so important? You see, fatigue crack, the growth of the fatigue crack or how it is enlarging, that happening exponentially. Suddenly it occurs. So, for example, you are inspecting the breeze at some point of time, and then after 1 year you plan to inspect. So probably you have seen there is no further growth of crack. Then again third year when you are going, you see the already fractured the member, okay, because of the exponential increase, okay. So fatigue crack is also very difficult to predict and also very difficult to measure, means how much fatigue growth has taken place, okay, unless you measure the vehicle loading, then only you have the better understanding that it is subject to this much of stress cycle. So there is a relationship between the fatigue crack growth and the number of stress cycle, okay, there is an equation. So for example, this is happening exponentially, and before going into the next inspection you will realize that there is a subsequent fatigue growth. So initially you will see there is a hair like crack, very minute crack. Then you are not able to see now fatigue crack are penetrating in nature. Penetrating means it is going inside the member, thickness, okay. So that is the dangerous part of the fatigue damage, or other member, corrosion or some other damage. You can see it is visible at the top layer, the member has been corroded, okay. So but in case of fatigue it is very difficult to detect, and the penetration is very difficult to measure unless you have laser light scanning system, okay. So otherwise you cannot detect. So this type of equation could be used, which is known as Paris rule, using linear elastic fracture mechanics, LEFD, okay. So dA by dN, A is the fatigue crack length and N is the number of stress cycle, so which is C delta K to the power M. Here C and M are the material constant, means it is to be determined by testing for that type of material, okay. It is vary with for steel it is defined, for aluminum it is defined, for wood it is defined, for concrete it is defined. So for each material you need to identify what is the C, what is the M, okay, those are constant, and delta K is the range of stress intensity factor which is given by this, so in the form of function of crack geometry. So this is to determine the increase of fatigue crack growth, and another rule is there or equation is there to determine the number of stress cycle the member is remaining. So each member is designed for certain number of stress cycle. You know steel is having certain number of stress cycle, it can prevent or it can resist probably 10 to the power 7 number of stress cycle, okay. Yeah, so this is given by this formula, accumulated fatigue damage, AFD, we say accumulated fatigue damage equals to summation of small ni divided by capital Ni. What is small ni? It is the number of stress cycle that the member has already experienced divided by number of stress cycle that the member has been designed for. So design stress cycle divided by number of stress cycle it has already undergone. So that will give you the accumulated fatigue damage. From this you can evaluate the residual life, okay, and then you can implement proper maintenance system. Now breeze owing motion, coming to breeze owing motion, how to convert the breeze to a weighing scale, that is the thing. So very simple way, you put a sensor, this is not a weighing kind of sensor, okay, this is just a accelerometer or any type of sensor you use to monitor the vehicle, breeze health, same sensor you will be using here. So what you will do, from this sensor you will get the response of the breeze due to the vehicle movement, okay, that is possible. Suppose displacement you are measuring, so because of the vehicle movement this much of displacement is occurring. Now from this displacement you should be knowing how much weight of the vehicle is traveling, okay. So you not only detect the speed of the vehicle, axle spacing of the vehicle, which type of vehicle it is traveling, but also what is the weight of the vehicle you have to determine, okay. So let's see simple illustration, okay. Suppose this vehicle is moving from here to there. So this is the response caused by this vehicle and this is measured by a sensor, this sensor. So from this response you have to determine the unknown weight of this vehicle. Okay. So how to determine? In civil, you must have gone through influence line, bridge influence line. So that is giving you the response of the bridge per unit weight of the load, moving load. So this vehicle could be considered as a moving load. Each vehicle is having some constant load, static load it is going. Only thing is that point of application is moving. So that's why we are considering this dynamic problem. Here we will think it as a static problem. Of course there is a dynamic part in the response. So we will discuss that thing later on. But from this response, if I know what is the influence line of the bridge, then we should be able to determine what is the weight of the vehicle. Simple equation. There is an observation, response, RKM, that is the measured response. This measured response is equals to theoretical response plus some error. Same, that has been discussed in the previous morning session. Okay. So now theoretical response is what? Response coming from the bridge, right? Coming from the bridge means theoretical, means if you know the theoretical influence line of the bridge, then if you want to estimate the axle weight of the vehicle, suppose there is 3 axle vehicle is going, so there is a summation of I equals to 1 to 3, NA, number of axle is 3. Then for each axle there is a defined axle weight, XI, 1, 2, 3, okay. Then if you multiply this with the individual influence line, for each axle there is a defined same influence line basically. The problem is first axle is moving, then second axle is entering, then third axle is entering. So the entry of axle on the bridge is on defined time. Therefore, when you constructing this response, you have to know which axle is coming first, then after how much time the second axle is coming, after how much time the third axle is coming. Then only you can accurately mathematically model that this is the time it is entering. So, for example, when suppose this is bridge, suppose this is the time first axle entered already. So at this moment, this bridge is subject to only one axle, right? So response due to this will be slightly, probably over here, okay, this response. Then what is happening? It is moving gradually. So then there is a entry of second axle, okay. So at that moment, both the axle are on the bridge. Then there is a movement of third axle. So at that moment, all the axle are on the bridge, okay. So that has to be mathematically modeled, okay. So this equation is there. You can change the influence line based on the information that entry time of each of the axle, right? So that could be obtained from the detection sensor. You can place a detection sensor over here. You can place another detection sensor at the bottom of the bridge on the exit side. So from there you can know what is the entry time of each of the axle. From this sensor also you can know what is the entry time of each of the axle. Now when you know the entry time, so you know the length of the bridge. So what you can do, you can obtain the velocity, right? What is the velocity? It is the length divided by time, defines in entry of that axle and passing of that axle, okay, or exiting of that axle. Then you can get the velocity of the vehicle, and from there you can know what is the sampling point defines between each of the axle, okay. So that can be done. So if you then minimize this error term between the measured response and the theoretical response, then the unknown axle weight x could be obtained using this equation. What is that equation? Here H is the influence line matrix and Rm is the response of the bridge due to that vehicle. So only two things are needed. One is the influence line, another is the response from the bridge. That's all, okay. So then the problem is there. Still there is a problem. This is also inverse problem. From the response you are trying to evaluate the weight of the vehicle. So it is an inverse correlation. So there is a ill-posedness also coming to this. So how to then overcome those things? That can be discussed. Okay. So ill-posed nature of the system of equation is there. Poor accuracy for closely spaced axle. Because of the ill-posedness, what is happening? When the axle spacing are closed, suppose always if there are more number of vehicles, suppose 3 axle vehicle are there. You can see 3 axle, these 2 and 3 number axle are very closely spaced. Right? When they are closely spaced, it is very difficult to segregate the contribution of each of those weight. So how to know their accurate weight? That is a challenging thing. Okay. So that can be done by using some efficient method. I will discuss. And then bridge vehicle dynamics is there, because there is a dynamic response fluctuation is there, and that will reduce your accuracy. Then inaccurate influence line. Suppose your influence line is inaccurate. Now how to obtain the influence line? That is also research domain, because theoretical influence, as I mentioned in the first lecture, that your theoretical thing may not match with the actual. So you need to identify influence line from the measured response. So before applying bridge OB motion, what you need to do? You run a calibration vehicle. Calibration means a vehicle with known axle weight. Okay, so that exercise you have to done for one time. Okay, so you measure a vehicle weight, go to the side, run it, measure the response. Now since you know the weight of the vehicle, from there again by solving similar kind of equation, you identify the influence line of the bridge. Once you are done with identification or calculation of that influence line, then you proceed with the implementation of bridge OB motion. Because for that bridge, influence line remain constant if there is no significant deterioration happen for that bridge. If there is a significant deterioration, then influence line will change. Because it is depends on the flexural rigidity, as you know. Okay, so those thing is there. Then transverse position of the vehicle. Suppose you have placed a sensor over here. Now vehicle is centrally moving. Then you see larger response. Now for some reason vehicle is traveling sideways. Okay, then response to that sensor will be lower, but vehicle is same probably, but it is moving away from the sensor. That's why its response changing. So that will cause erroneous. So what you need to do? You may place more sensor here, here, here. So then you can take into account. Yeah, something happened. Yeah, thanks. So you can place many sensors across the transverse direction. Then integrate information from all of these sensors to have a robust measurement. Okay, so those can be done. So I will discuss few of them because time is very limited, and of course I need to also give some demo. So what is you need? This is the slide which discuss about the influence line identification from the real measurement. So what you need to do? First you need to run a calibration vehicle, as I said, with known axle weight. Okay, for example, I know the vehicle weight for this one. Then I am running it. So this will be the measure response which is known. Here A multiplied by I. Here it is I means influence line, which is unknown. Again you need to identify this influence line. And A is the vehicle information matrix, which is this matrix. What is that? First there is a entry of first axle. Okay, W1 is the first axle weight. So you see in that row there is only first axle weight. Then there is a entry of the first axle weight moving slightly further like this. So you see W1 is moving like this across this. Then there is a entry of second axle weight after certain point. Then entry of third axle weight. Okay, so this is going on. Okay, so this is matrix, the vehicle information matrix should be constructed based on the calibration vehicle, because you know the weight of the vehicle, you can do it. Okay, then this can be minimized again by identifying this I. So how? This A transpose A inverse, then A transpose Rm. Here Rm is the response, that is you are measuring, and A is the vehicle weight matrix or information matrix. So all the things are known, so I can be known. Okay, so this is time domain method. And then frequency domain also, you can convert the vehicle response, this is the response, into frequency domain. Just Fourier transform, apply Fourier transform, and then you just go to this domain. Then you try to identify the influence line. Okay, it is also easy. So you will see, if this is the response, suppose this is the response from 4-axle vehicle, this is 3-axle vehicle, this is 2-axle vehicle. Okay, then this is the influence line obtained from the by using this equation. Okay, and for 4-axle, 3-axle, 2-axle. Now, should the influence line be dependent on the vehicle type? Should not be, because influence line is a fundamental property of that bridge. It should not be dependent on the vehicle, right? But here you can see it is defined for vehicle because of the dynamic component. So if you remove the dynamic component, you can use high pass filter to remove the dynamic component. Then you see this is the static component, a static weight. So now you can see for static, all the vehicle are giving similar influence line. Okay, so that can be obtained. Okay. Then bridge wave motion can be implemented using the base theory also. Similar, because there is a measurement, okay, and you want to estimate the unknown, okay, so you can use Bayesian as well. But here we will not use any prior information, because no prior information available. Only from the measurement we will identify what is the axle weight of the vehicle. So no prior, non-uniform prior we will use. Okay, so this is the same equation that has been discussed in the bonding session. Z equals to hx plus b, and then prior information x equals to x bar plus w, deterministic mean, and some probabilistic variation. So objective function is this. Then maximum and posterior map, we say dj by dx equals to 0. Then this equation can be used. Now here there is a prior, but we will not have any prior information because each vehicle is unique. I don't have any prior information, right? So I only have the response. From the response I have p-value. So I can get rid of this. So this is called non-informative period. So x bar, that is your updated kind of axle weight, is equals to this equation, P H transpose R inverse Z. Okay, independent of period information. So this is the posterior mean, this is the covariance. So using Bayesian, not only you can estimate the axle weight, but you can also estimate what is the uncertainty or error in estimation. Okay, so that is the beauty. So what you can do, suppose in the bridge there is a two types of sensor. Here I have placed detection sensor on this side, and then I have used another sensor which is contact displacement gauge at the center, middle. The purpose is to measure the displacement, and here the detection sensor purpose is to measure the entry and exit time of vehicle. So let's okay. So okay, no example has been provided. Okay, I have skipped this. So for example, this is the response measured by the vehicle. Okay, this was the 3-axle vehicle traveling on the bridge, and this was the response. From that response, using bridge wave motion, this is the estimated gross vehicle weight. GVW means gross vehicle weight. What is that? How much? 11.76 ton. What is the actual weight? 12.6 ton. So almost similar. Okay. And what is the axle weight? Axle weight we can see actual are shown as the dashed black line, and then red dotted line are the mean. So there is a discrepancy, right? Why? Now gross vehicle weight is a combined vehicle weight. That is easier to identify. Now to separate the contribution of individual axle weight, that is difficult because it is an inverse problem. Ill-posedness is there because dynamic component is there, right? So we need to solve the ill-posedness of the problem and increase the efficiency of the method so that our axle weight identification could be improved. And this is the uncertainty, standard deviation of axle weight. For all the cases, you can see there is a although the estimated gross vehicle weight was close to the actual gross vehicle weight, but there is a discrepancy in the axle weight identification for the case of closely spaced axle. Okay, for example, here number 2 and 3 are closely spaced. You see the larger error is number 2 and number 3. For example, here two vehicles are running parallel, two vehicles at the same time. So this second and third axle closely spaced, so their identification is difficult to separate out the contribution of these two. Okay, similarly there is a inline driving condition, two vehicles, 4 axle and 3 axle running in line, same line. So you can see there also, when there is a closely spaced axle, there is a larger error in identification. So what we can do here, we have implemented additional information. What is not a prior information? This is additional information. It is not a prior. What additional information? Because from the detection sensor, you are having the information of entry time of each of the axle, is not it? So from there you can, if the entry time is very closely spaced, so that information suggests that your vehicle axle are closely spaced, right? So two vehicle weight closely spaced means, if suppose I am placing 50 kilo over here, 50 kilo over here, and there are two wheel over here, then what do you think? How the weight will be distributed? So this 50 kilo usually distributed among these two, right? Probably, because they are closely spaced. If suppose one axle over here, another axle over here, then we can say, since this axle is just beneath the weight, then lesser weight will be carried by this axle, right? And lesser weight will be carried by this axle. But since suppose both are closely spaced, like this, two wheels are very close, so whatever weight that is coming over there are equally shared by both the axle, is not it? Suppose 3 axle vehicle moving, there is a one axle at the front, weight of the engine and other thing are going there. Rest of the weight is going at the rear axle. Now rear, there are 2 axles closely spaced. Now what do you think from the common sense? If I apply a weight over there, what will happen? Both will share similar weight, kind of. Okay, there could be differences, but not much. More or less similar. So that information we can use as additional information. So whenever there is a closely spaced axle, we assume that whatever weight coming to this are equally shared by this and this. Similarly, equally shared by this and this. Equally shared by this and this. Because in this scenario, for example, this is inline driving condition. 4 axle vehicle is running forward, followed by 3 axle. Therefore, there is a larger peak, then there is a smaller peak. Okay, both are running inline. Okay, so there are 3 sets you can see: first and second axle of track 1, third and fourth axle of track 1, and second and third axle of track 2 are closely spaced. So we can use 3 additional information here in the form of D, that first and second axle having closely spaced. Closely spaced means weight are same. So suppose weight are same means, suppose this is equals to some value, some weight, right? It is, let me clear. So suppose this is the first axle weight, this is the second axle weight, they are same. We are not saying the exactly same, we are saying that this equals to some error. Again, we are using the Bayesian or Gaussian distribution, we can measure or you can model the error function. Okay, this x1 minus x2. If x1 equals to x2, similar thing, then what will happen? This is 1, this is minus 1, right? It is coming, and some weight. So that is what is written over here: 1 minus 1, 1 minus 1, 1 minus 1. Okay, so that means they are having similar weight. Okay, how much variation is there? V2 we have introduced, which is given by this R2, covariance matrix R2. We can regulate. Not only we can model this, we can, by defining lesser error, we can say almost equal weight as here. By defining higher deviation or higher error, we can say it is fluctuating by 20%, 30%, whatever it is. Okay. So you have the freedom in this R2. Okay. So the equation now has changed. Now the posterior mean is this and covariance matrix is this. There is a additional information term D and covariance matrix R2 is coming. Okay. So by incorporating this, can the measurement be enhanced or improved? So you see now this blue dotted line are corresponding to with additional information. WAI means with additional information. So you see they are closely correlated with the true value of axle weight. So you can improve the accuracy. So this type of methodology you can use for real life problem also, not only this problem, for any other problem. Just use the common sense, integrate it into your mathematical framework. Okay, that's it. That is what it is needed. Okay, you don't need rocket science. Okay, to solve any complex problem. So by using this simple kind of thing, you can improve your efficiency of algorithm substantially. Okay, now you see the this is the standard weight, standard deviation of axle weight, that also reduce when you use the additional information. Okay, blue line is at the down. Okay, so it has reduced. Okay, so this is one example. Okay, then there is another thing is that segregation of dynamic and static part. You use some high pass filter and then you take out the dynamic component. Then you model the dynamic component appropriately. Usually in Gaussian, when you are modeling, we assume that the noise is random. It is the white noise. We usually assume. White noise means it is very random. So that means it is uncorrelated. Diagonally it is there, off diagonal term are all zero. But if it is having some cyclic component means the response at a particular time instant is correlated with the next or subsequent, because it is cyclic nature, right? So it is no longer uncorrelated or independent of each other. So you have to then have this non-diagonal component also. When you model the covariance matrix you cannot assume that it is independent and identically distributed. You have to assume then actual covariance matrix. How to identify actual covariance? You obtain dynamic component, the fluctuation part. Then from there you obtain the correlation function. Correlation function you can see it is going like this. So from this you can also suggest that there is a significant correlation. If it is random, if you evaluate the correlation of a white noise, you see from 1 to 0 it will come down, no correlation, okay, because it is random, okay. So this matrix could be changed and then subsequently your R matrix, instead of uncorrelated, it will have off diagonal component, okay, that can be done. This way also you can also improve your accuracy, okay. Here it has been discussed, okay. So this is kind of research domain, I am not going, okay. If you are interested, you can let me know. Okay, these are some kind of this is one of the example of axle detection. Okay, because I have mentioned about axle detection, you can see entry side, you can see peaks. Then exit side, there are similar peaks. Now, if you develop algorithm, now you can use AI and machine learning algorithm to identify the peaks automatically. Okay, whenever vehicle passes, there will be peaks generated. You know, identify those peaks and label this 1, 2, 3, 4, 1, 2, 3, 4, and from there, the entry time and exit time differences, you can determine the velocity. You can determine how many axles are there, what is the axle spacing of the vehicle, all other information you can determine from the detection sensor, except the vehicle weight. Except vehicle weight, all other information from the, or which lane it is traveling. Suppose there are multiple lanes on the bridge, then you have placed several detection sensor. Okay, then in this case, you can see in the Ladder 2 detection sensor, there is a peak. Ladder 3, there is a peak. Ladder 4 and Ladder 5, there is no peak. Probably that means the vehicle was traveling to, traveling to lane 1, probably, right? It was not traveling to G4 or G5, right? So it was traveling to lane 1. So you can also say which lane it is traveling by identifying the peaks. Okay. And from the acceleration also you can determine the displacement by double integration. Okay. If you have the acceleration data, for example, these are the acceleration data, vehicle induced acceleration, and then by double integration you can also determine this displacement and velocity. Okay, that is also possible. Okay. So in summary, what you need to do? First, you need to identify the influence line of the brake. Once it is done, then you need to run any target vehicle, unknown vehicle is running. You identify the peaks from the detection sensor. Okay. Then obtain this information. What is the speed of the vehicle, number of axle of the vehicle, axle spacing. Because these are required in your algorithm. Speed is required because you need to identify the entry sampling point difference between first and second axle. How to? Because it is dependent on the speed. Otherwise, if speed is fluctuating, then what will happen? After entry of first axle, after certain time second axle entry, and then third axle you don't know when it is entering, or second axle when it is entering. So you need to identify the speed of the vehicle accurately. Also number of axle, because you need to identify axle weight of all the axle, and also you need to construct the influence line matrix. For each axle there is each influence line vector, okay, in the influence line matrix. So these are the information that is required always. Then based on this you can have this is the measure response due to this vehicle, unknown vehicle, and then from this information you can construct now you can resample. Now this influence line was calculated based on the calibration vehicle, which was run at certain other speed, probably 60 or 40 lower speed. Okay. Now this vehicle is running at defined speed. So your influence lines could be recalibrated based on the speed difference between this and this. Okay. So that is what it was done over here. Now based on the number of axle, then influence line matrix you have to construct. Okay. This is the influence line matrix kind of. Then from there you just solve the equation and identify the axle weight. So that is as simple as that. Okay. So I will end here, and then probably quickly we will solve some one problem. Okay. Then we will continue in tomorrow. But there is tutorial class as well in the first session. Okay. So let's go to MATLAB. 2 minutes break. Okay, you can take if you want. 2 minutes break. Okay, so this is the sorry, is it visible?
Last one, use slide.
Share again?
Again, use slide super.
Oh, okay. Ah. So this is the problem statement. You see, a coin has an unknown probability of landing head, okay, denoted by theta. Then we assume no prior knowledge about theta. So the prior distribution is uniform over 0 and 1 because you are not using any prior information. Okay. Then you perform 10 independent tosses, okay, of that coin, where the true probability of the head is theta true is 0.7. Okay, means it is a kind of biased coin. Okay, right. But in the initial assumption, we are not using that thing. We are just assuming that we don't know that biasness. Okay. Now, what is your task? Write the likelihood function for a single coin toss given theta and extend this to the likelihood for a sequence of tosses. So what I am suggesting, suppose initially you do first toss, okay? Then based on the result of first toss, the Bayesian method, you will update your prior information. Eventually first, when you start the test, toss of coin, then you are assuming that equal probability. Okay, it could be head, it could be tail, no prior information, right? It could be 0 to 1 anywhere, right? So then, suppose in the first toss, something is coming up like head or tail. For example, if it is head, then probability of getting head will increase if it is head. If it is coming tail, then based on the observed data, your probability of having tail will increase, is not it? So subsequently, you will do this exercise 10 times, one by one, and by the end of each test, you will update your that theta, that is unknown probability of landing head, unknown probability of landing head, theta, you will update it after every test, okay? And that will update your probability of head, okay, based on the observed head or tail. Okay, is that clear, the problem statement? First, you don't know what is the probability of, true probability of getting head from that coin. It is there that it is true probability is 0.7, but we don't know, right? Then we will do 10 tests, and after each test we will try to update our understanding of getting head or probability of getting head. Okay, so let's go to the MATLAB. You have taken a picture of this now? Okay. See, so n is equals to 10. Is it visible? Okay. Then true probability of head is 0.7. Is not it? Then there is a simulate coin toss. So RNG default, I have given RNG default. What is the meaning of that? Sorry. Oh, this is probably I have to increase the font size, right? How to increase font size? Probably in setting.
June, sir. June. But
Like this. So here you can see there is a RNG default. So because randomly I am simulating the toss. Okay. You see the next line. RAND 1 to n means it is a simulating a vector, okay, having some number, okay, random number, which is less than 1 actually. How many times? For 10 times. So length of the vector is 1 by 10 basically, 1 by 10, means it is a row vector, okay. Then in this state, data is equals to RAND less than theta true. So that is considered as a, if it is less than 1, that is head, and if it is 0, it is tail. Okay. Then you are giving F print of this, that is the toss outcome. 1 equals to head and 0 equals to tail. That will give you. Okay. Can you try this code in your laptop? What you are getting up to this point? You will see this is the toss outcome. Okay. So in the first toss, it is 0, means it is tail. In the second, it is also tail. In the third, it is head. In the fourth, it is again tail. Then all are head up to 8. Then ninth, it is tail. It is tail. So based on this, so this is RNG default. The meaning of this is so that you can reproduce your result. If you don't provide RNG default, then what will happen? Your random number will be regenerated with some other number. So only when you provide this RNG default, then only you can reproduce your result whenever you are running that code. Okay. If I omit this, every time I run, I will get defined outcome. Yeah. Okay, okay. So, yeah. Sorry? Yeah. Already done? Okay. This type of graph you are getting? Are you getting this type of graph? No? So try to run this code. Shall I minimize this or not? Yeah. Oh. Yes, yes, yes. Yeah, I think fine. Perfectly fine. Perfectly fine. Yes. I think you did it correctly. Okay. Wow, very quick. Yeah. So what is the meaning of this 10 subplots? All of you are getting same result? Now at the end of 10 toss, what was the probability? What was the mean? Those who have already done, so what was the mean of this? This is not close to actual true mean, right? True mean is 0.7, right? So since initially you see the probability of having head is very low, is not it? Then as you proceed with your tossing event, then in the second also, because you got tail, in the second toss you got tail, so your initial understanding did not change much. Okay, it has slightly changed, but still not changed much. Then in the third event, when you got the head, it has changed by large amount, is not it? Then again at the fourth toss, you got tail, so it was further shifted again on this side. So probability again reduced. Then again in the fifth, sixth, seventh, eighth, all you got head. So your probability again shifted towards higher probability of getting head, right? Then 9 and 10, again you got tail and tail. So your probability slightly reduced, right? Is not it? All of you got this. Then I will show another thing. Or there is a problem? Yes. Similar, okay, that's great. Then I have written another code where I have run this for n equals to 40. N equals to 40. You can also write same thing. This is just animated the outcome, how it is changing for each iteration. So if I run this, so you see after every toss, the output, that is the uncertainty of getting head each time, is changing over time. Now, the longer you are doing the experiment, the mean of that theta should reach to the actual outcome or our true value of theta, which is 0.7. So, your probability at the end of significantly large number of tests should be around 0.7. Okay, so it is how much? Okay, probably I have not used that again RNG part. Let me do that. The default. Now let me run this. You see, this is one simple illustration of Bayesian method. So at every event, based on the outcome, it is updating the information of uncertainty of theta. Okay. So probability. See, when I increase, it is going further close to 0.7. So if I do this exercise for 1000 times, probably it will align with the true mean, okay, of 0.7. Is not it? So you can check, okay. Okay, so tomorrow we will continue doing some other exercise. Okay. Any other questions? Okay. So I am ending the session. You can just check the code I am sharing. The first one or second one? First one. Minimize. Going down.